You have to help each kid with autism lead the best life they can. That's normal life for them. Most autistic kids will be very talented in some area, and you got to figure out what that is. Because if they're empowered in that domain, they feel liberated inside because they're expressing their talent in that domain. Families and teachers have to deal with a lot. But if they understand this, that this is not irreversible damage of the brain, that's why we're all in this, because we know that this is a tractable problem.
Welcome to the India Autism Center podcast. You know, this is your space for meaningful conversations about autism awareness, inclusion, and support for neurodivergent individuals. I'm your host, Sakhi Singhi, and today's episode is a special Ask Me Anything featuring an expert whose groundbreaking work in neuroscience sheds light on the intricate relationship between brain plasticity, cognitive flexibility, and autism. I am so happy that we have him here today to share his insights and provide us a deeper understanding of the neurological basis of autism and its impact on daily life. Thank you so much, Dr. Chattarji, for joining us here today.
Glad to be here. Thank you, Sakhi.
Finally, this happened. And I want to start with the first conversation about your background. It's just fascinating. You began in physics, you've transitioned into neuroscience. Every time I talk to you about academics, you tell me to delve into it, and then you tell me not to delve into it. Yeah. And then I want to know what led to your journey in studying autism and what has been the surprising discoveries in the process.
Sure. So yeah, my transition from physics to neuroscience was exciting and sometimes unnerving. Because I could not do that transition in India in my time when I was a student. And so I studied physics in IIT Kanpur. Okay. And at that point, I had a clear path ahead in physics if I wanted to do a PhD. But I jumped the ship and I applied only for biophysics in the US, which was a bit of a craziness. I took a risk and I got into Johns Hopkins in biophysics, which was my dream school. And once I got there, I got very lucky to meet somebody called Terry Sinowski, who was a computational neuroscientist, very famous, neural networks guy actually, who actually did his PhD and then his postdoctoral research with two people, John Hopfield and Geoffrey Hinton, who got the Nobel Prize in Physics last year. So that was the lineage.
Wow.
And he was a strange person. He was very, very innovative. And he allowed physicists to come into his lab to do biology. And he had biologists doing computational modeling. So basically in that lab, nobody knew what the hell they were doing. But it was always very ambitious, high end. And from him, I learned that I could do this. And I, coming from physics, was promptly put into projects which are entirely wet neuroscience lab-based stuff. And at that point, I didn't know I was going to work on stress or autism. But what I did focus on at that time are two things. One is the philosophy of how do you go after neuroscience. It's a complex question, understanding the brain, especially the diseased brain. And so you've got to break it up into smaller pieces to understand the pieces first and then put it together. That breaking up into smaller pieces that are bite-sized that you can grapple with is basically what is called a reductionist approach. Don't take the whole thing and get overwhelmed, take little pieces. And if you take a reductionist approach, which is what I learned from Terry, that you can study the same problem at the behavioral level, networks and circuit levels, then single individual brain cells or neurons, their connections, synapses, then the molecules, then the genes, right? In any of these levels, there's so much to discover, and then you can put it together. So my focus at that point was on the connection between neurons, the synapses. And that was an easy entry point for me because a lot of it was looking at electrical signals. And I had a background in physics. I was very scared of biology because I never did well in biology or chemistry. But so that was my entry point. And then along the way, I learned all the basics of how synapses encode information. And much later, I started working on stress. And even later, I worked on autism, which we'll talk about later.
You know, many of our listeners, they're curious about the neuroscience behind autism. What happens neurologically in autism and how does that differ from how a neurotypical brain would function?
Yeah, I think the first thing to note is in autism is not like, which are called neurodevelopmental disorders, which means as the brain develops in its early days and early months and years, how the brain is built and put together, the connections that are being formed, do not happen in the typical fashion, okay? And as a result, the brain is wired differently over time and reaches a point where all the pieces are there, nothing is lost except the connections and the pieces are working slightly different.
Okay.
Right? Why do I say that? That should be distinguished from neurodegenerative disorders, where the aging brain or dementia, Alzheimer's, Parkinson's, where neurons and their connections are damaged permanently and irreversibly, and there's no way back most of the time. That's not the case with autism. It's a young brain that's developing and forming somewhat differently, sometimes quite subtly differently.
Okay.
So everything is there for you to tweak and massage and get it back to a typical functioning sort of status, right? So that's the difference. And one can, again, focus on all aspects of autism, from behavior and networks in the brain, or the individual neurons and their connections and molecules. And one can choose to look at all of these. But much of the focus of autism research in the last 20, 30 years has been on the connections between neurons, the synapses, which we will talk about. And so the connections are off a little bit, deviating a little bit from the standard functioning, but they're not damaged or dead. So they're functioning fine, but little differently, which means that if you understand that process well, you have a way of tweaking it. Yes.
Got it. Which actually ties into the next question about your research in brain plasticity. And what is brain plasticity in autism, and can it be harnessed to improve cognitive flexibility and learning in autistic individuals?
Yes, that's a very good question. So I think let's take it in two pieces. Okay, one is the term brain plasticity. The brain is constantly changing with experience.
This is something that's become a buzzword.
Yes.
Every YouTube self-proclaimed motivator talks about neuroplasticity, and
That's
I actually want to know more about it.
Right. Yeah, I wish I'd sort of found a company earlier, but this is what I've worked on all my life, actually.
Yeah.
It's right from the beginning. So the simplest way to understand this is that, when we are born and the young brain has few connections and it's just forming, in mammals, especially in humans, the brain develops over many years. First, the brain cells are born. Then they're finding their way around different areas of the brain. Then they're forming connections.
Okay.
So that means that there's enormous plasticity. I mean, it's malleable. It's like soft clay that you can sculpt any way you want. That's plasticity. It's a catch-all term for saying it's not static, right? When a zebra or a deer is born in the wild, they come hardwired with lots of responses.
Yeah.
Because if they're being chased by a lion, they don't get 3 chances to learn. If you don't learn on the spot right then, if you're not ready, you're somebody's lunch, right? So a lot of it's instinctive, hardwired. They have to be that way because they have to survive from day one. Humans, on the other hand, or mammals, higher mammals and primates, we come with the basic skeleton of the genetic blueprint of the growth of the brain, but much of it then happens post-birth, postnatally, with experience. Parents, family, communities, everything. So, and that takes a long time. That's the price we pay for taking time to grow into the full brain. But that's also the opportunity that you can sculpt the brain with experience and things. So that fact that it's not a static entity, it can adapt with experience and change being the key term, plasticity is capturing that. So there can be good plasticity, which is the brain grows, it forms the right connections, it has all this potential in full bloom. Disease will then affect that plasticity. Okay. And I would call that bad plasticity. It's still changing, but as a result of disease, and it's becoming detrimental. So there's good plasticity and there's bad plasticity. And the job for us is to use what we know about good plasticity to counter the ill effects of the bad plasticity. Right? But the plasticity in itself means that the brain can change because of genetics, because of disease, but most importantly, because of experience. Yeah.
So the brain essentially is always a work in progress.
Right.
And there's really, so when people talk about early intervention being really important, is it just because, so to speak, the brain, the clay is just softer then?
Absolutely.
But that doesn't mean that intervention becomes kind of meaningless after a certain age.
No, not at all. In fact, there's a notion that, after the teen years, you cannot change anything. So one of the biggest examples, striking examples of change, of that extreme plasticity, if you will, is there's an area of the brain called the hippocampus, which is crucial for learning memories of facts and events.
Yeah.
The fact that I know your phone number, the time and date of this meeting, this location, everything is hippocampus, right? There's a part of the hippocampus called the dentate gyrus. It's just one area where new cells are born and they come in and get integrated into the circuit. In adults, not in a developing brain, that far out. And it's been shown that even people in their 50s, there's new brain cells formed in them in that part of the hippocampus, which gives me great hope. I probably have here. But the fact is then that the brain is dynamic and can continue to change well into adulthood.
So this plasticity actually helps with learning and daily life, and it helps pretty much everyone. It's not just exclusive for...
It's for everybody, yeah. It's a fact of life. It's just like if you're living, you're breathing. If you're living, your brain has plasticity. It's as simple as that.
And it's not different from that of an autistic.
No,
for an autistic brain, it's the same?
Same, absolutely. The rules are the same. The ingredients are all there. But one will, depending on where the aberrations are, the connections are somewhat off keel. And that can depend on specific types of synapses in specific circuits in the brain. See, autism is caused by genetic perturbations, right? It has a genetic root. So the same gene could do different things in different parts of the brain, of language and vision and thinking and rational thinking and memory. So as the gene has its effects, different parts of the brain and their connections will have something that is affected, and some places it may not affect. When I say affected, in some cases the synapses are better off, they're hyper-connected. In some cases, they're not enough connected. And so some parts of the circuits may function very well. You'll see autistic individuals are phenomenally good at certain functions. When they focus, they can be good at math, can be good at programming, they can be good in art, they can be good in music. That means those circuits that serve that function are actually far above normal, right? But conversely, there are some areas where those circuits are not functioning the way you expect them to function. They're dormant or they're just not there, and one can make them go there, right? So it's really a change of balance in these connections, that's all. And as long as the plasticity is there, and you know how to access that plasticity and make it work for you, you can change those balances as well.
Got it. Yeah. And also, but I'm assuming for individuals with profound disabilities, like profound autism disabilities, and with comorbidities, is there a difference in how the brain is functioning?
I'm glad you brought that up. So when you talk about non-verbal autism, that's a tough one, right?
Yeah.
Because so much of our lives are social, right? Social interactions, and language is a key part of it, right? So if there's no linguistic communication even with the parents, that takes away the opportunities that you can use with language and communication, right? But it's quite obvious sometimes that despite not having language, they do have ways of communicating, right? So I think we'll come to that a little later.
Yeah.
But I think understanding brain plasticity and how it gets gone awry is vital, right? And that's where the psychologists, the psychiatrists, and the family's understanding of daily brain function and then the underlying science behind it, which is what we do, that communication has to be strengthened. Because increasingly we understand how these circuits are off and how experience can overturn that. And overturning that with experience is entirely the community and the family and the friends, their job. But if they're armed with the information of the kind that we gather, then I think both sides benefit from it, right? That's the job. Yeah.
So my next question is that memory, as we know it, plays an extremely crucial role in learning in daily life. As you mentioned, you remember this meeting, you remember to come here, you remember my name. How does autism affect memory, and are there any strategies or therapies that can help improve emotional regulation and recall? Yeah.
So, let's again take it in two parts. One is the basic science of the plasticity underlying memory formation.
Okay.
So you have an experience. That means it comes to your eyes and ears, whatever. You hear something, goes to maybe the hippocampus for facts, the amygdala for emotions. But the basic thing is that when some experience hits the brain, some thousands of brain cells will get activated. They'll get electrically active and they will fire away. As a result of that, these synapses that are connecting these neurons are getting activated. And that activity, specific pattern of activity in these tens of thousands of synapses, maybe hundreds and thousands of synapses, makes them, elicits plasticity, which is changes the strength of those connections. And the common knowledge is that the synapses get stronger in some pattern. That change mesh of synaptic strength in that network is the physical embodiment of the memory. It's getting stored in those synaptic connections which got stronger. Right? That's your memory. And then now later on, when the similar stimulation comes, I see you in an autism conference, or I see you in the neighborhood where we first met, it triggers that I know this person somehow, right? Or I know somebody
Correct.
I met together. So then those same synapses will get activated again and you recall the memory. So that's brain plasticity and formation of memory. Now, if you understand that if synapses are not functioning the same way and their balances are a little different, then the act of that memory formation, the plasticity will not be the same. They may get too strong, they may get too weak. And so on. Now, then comes the question of emotional regulation, right?
Yeah.
So emotional memories tend to be very strong, right? You don't need multiple experiences. Something bad or good happens, you'll remember it for life. That happens in the amygdala, which is what I work in, the neighboring structure next to the hippocampus. In our own lives, we know that remembering a fact is quite challenging because we have information overload. So the hippocampus is always struggling to remember things. It needs repetition. The amygdala, on the other hand, is designed to remember things very well, because emotional events are often once in a lifetime, sometimes life-threatening, and you better remember it, otherwise you're not going to survive. So boom, that happens very quickly.
Got it.
Now, some emotional memories, if they're traumatic, you have a tough time forgetting it, right? Flashbacks and PTSD, things like that. So if this balance goes off, you could reach a state, which is what my stress work shows, that factual memories coded with the hippocampus are going downhill because the hippocampus gets damaged with stress. I've also shown at the same time that the same stress in the same brain in the amygdala makes the amygdala connection stronger. Now, this is the same experience, weakening the connections in the hippocampus and make them stronger in the amygdala. What will happen? You won't remember facts and events, but you'll be highly emotional. You'll be highly fearful, highly anxious. That is all the stress disorders. And in some cases, that happens in autism too. And that's what I've studied in Fragile X, high social anxiety, learning disability. So you see, when I'm talking about this, it's really a balance between the amygdala and the hippocampus, the cortex, and balance in synapses within those structures, right? Now, emotional regulation, you can imagine if I give you a phone number, you won't remember it, 10 digits, right? No reason to remember it.
No.
If I say, but this is the doctor's phone number where your mother is admitted, you damn well remember it, right? So if you give a little emotional sprinkling, the same factual memory gets stronger. So there is an interaction between the two, right? So you may want to spruce up memories, strengthen them with emotional inputs and make it stronger. That's one way. Or you may not want to do that, because if emotions are beyond regulation and if somebody is highly stressed, then that clouds cognitive function, right? And then you must regulate the emotional aspects of it first before you can go even to rational thinking and cognition. So this striking of the balance is vital. And that changes from individual to individual. So each autistic individual is different in their makeup.
Correct.
Each individual is different in their makeup, right?
Yeah.
What I find stressful, you might not find stressful at all.
Right.
So we need to understand that the same thing is true for autistic individuals. And that's where parents and friends and families' understanding of that individual's makeup, right, in terms of cognition, balance with emotion, is vital, because one rule will not fit all. Right? That individual understanding is vital for this.
So I am actually one of the most frequently asked questions from parents, and this is a question that we have for you, is, can my child with autism lead a normal life? And based on your research, what does long-term development look like for autistic individuals?
The answer is absolutely yes. Okay. And let's take the term normal life, right? I think that's where
the problem is.
Right?
Right.
In your eyes, you know my work and my life a little bit. In your eyes, honestly speaking, my life is abnormal.
Yes.
Right?
100%.
I'm doing 16 hours a day. we do the same experiment over and over again. We fail repeatedly and we keep doing the same stuff.
Correct.
Right? It's almost like repetitive behavior in autism, right? We don't socialize. Our social skills, not mine, but most of my colleagues' social skills are very poor. They don't, in MIT where I used to work, my friends used to say, 70% of these kids in MIT are...
They haven't seen sunlight, I think.
or they have some sort of Asperger's score.
Oh, yeah.
Right? They're not making eye contact and all of that. So I think normal is highly context-specific, individual-specific. So I think the first thing one has to do...
Did this take you a while to understand? Or this was something that you established
very
very
early? I have
early?
a very normal wife who was always there to point out that this is a weird life, right? So I had that bearing. But, I wanted to do it. So you have to give up a lot to get to this kind of science, right? But I understand when kids come in, I always demystify the process and tell them that this is not normal life, right? So going back to your question, so for you have to help each kid with autism lead the best life they can. Whatever is in their ecosystem, in their mind, and life that they enjoy and can flourish, that's normal life for them, right? Number one. If you try to fit it into a standard model and say they must be this, that's a disaster for a neurotypical kid. That in our society, everybody's forced to become an engineer or a doctor, right?
True.
It's a disaster. Same thing holds for them. But once you figure out what their strengths are, most autistic kids will be very talented in some area, more often than not, right? And you got to figure out what that is. Because if they're empowered in that domain, they feel liberated inside because they're expressing their talent in that domain. It may have come at a cost to other functions, but unless you empower that angle, there's no game. Once you let them flourish in that window, the stress of not being able to do that and being forced to do other stuff will come down. And then the other circuits that may need some nourishing can happen in an incremental, understood way, that this individual have a pace of learning, a pace of dealing with it, and that understanding has to come from the parents and immediate friend circle. One of the big things they're often asocial, no eye contact, Fragile X, I've worked with Fragile X, no eye contact, social anxiety is high. And yet they don't avoid. The first time I met Andy Tranfaglia, the son of FRAXA, Fragile X Research Foundation, medical director, and Mike Tranfaglia and Katie Clapp's son, that was my first exposure to a Fragile X kid in MIT. They had brought him to meet me in the lab, which I thought was a little scary because, this place, how would he deal with it?
Right.
He came in, he was in a room of this size. I was working in an experiment. He came in, I thought, he should not be forced to come in.
Yeah.
He came in. He did the Fragile X handshake. He couldn't make eye contact, right? He was stressed with an unknown person in a strange setting, but he didn't leave the room. So he wanted to find out who I was, but the social anxiety was overcoming. And I knew that. So I never made eye contact with him. The full conversation, I talked to him like this. But Andy and I became friends because I understood that Andy had other things that he could do and he was enjoying it. So in each case, one has to titrate, and social anxiety may be one of the reasons they cannot learn that fast. Because how do you go and learn from a stranger in a strange setting when anxiety and the amygdala essentially is overrunning everything? So if they want to stick with a routine that is predictable every day, the same thing, that is because of that no surprises. Don't surprise the amygdala, let it be, calm it down, and then things will happen. It's incremental, it takes patience, but if you want to unearth the other abilities that are getting clouded or suppressed by anxiety, you got to let that happen in a way which is smart. And then you'll be surprised to see how much there is in there, right? And this makes complete sense from the neuroscience perspective. I completely understand what's happening. But I think families and teachers have to deal with a lot.
Yeah.
Right? But if they understand that this is not irreversible damage of the brain, such as Lou Gehrig's disease or Parkinson's or Alzheimer's, it's not that. That's why we're all in this, because we know that this is a tractable problem. This is something we can fix, right?
Correct. Yeah. There's a lot of discussion about the impact of stress, and specifically stress for the autistic brain. Can autism be triggered by stress, and how do you think autistic individuals react to stressful situations versus neurotypical individuals in their brain?
Great question. That's my area of research. I used to work on stress in general, what stress does to emotions and cognition. And then everybody said, you should come and do this in Fragile X.
Yeah.
That's the same problem. So if you think about the stress disorders, it's triggered by stress, traumatic stress, chronic stress. But it's an experiential perturbation, right? It's happening in the outside. And in that work, I showed that the same stress can upregulate emotions and downregulate cognition, and what the neural basis of that was.
Okay.
Then I thought, okay, that's all experience. But genetics does that too in autism, right? High fear, high social anxiety, unstable mood, cognitive learning disabilities, right? I said it's the same thing, but because of the genetics. So that's what got me interested. The effects were the same, but this is now from genes upwards, right?
Yeah.
And there, the first thing most of the doctors wanted me to look at is how does stress affect, an autistic individual. So there are two answers to your question. Does stress cause autism? Not possible. It's got a genetic basis. Can stress exacerbate autism symptoms? Yes, right? Because the first thing is, they cannot deal with a stranger, right? You don't want anxiety, you don't want stress. So even seeing somebody in the room that you don't know can be stressful. Not for me and you, it happens to some of us too, right?
Yeah.
And that stress, what it does, it causes surge of stress hormones, the amygdala takes over the brain. And at that point, asking the cortex or the hippocampus to function normally is impossible. It's just not fair. So I think lowering the stress, which means predictable environments, known faces, known people, known routines, right? And if there's novelty, in bite-sized pieces, slowly, incrementally, right? And anything the individual doesn't like or is clearly showing displeasure with, take it off, right? Because that person is doing it based on his or her rules of the game, not yours. Right? That's the whole thing. So it's a game of patience, but stress is a huge factor. Yeah.
So before we wrap up, I actually really want to ask you this question, and then we have this insightful short segment, and I think you're the best person to answer this. There's a lot of information and misinformation about stem cells, Professor Chattarji, and I'm sorry, I'm going to have to ask you about
absolutely,
it.
Yes.
Can you please help us through what exactly is this stem cell therapy that people are talking about?
I've seen this. In fact, now when you ask me this question, I'm ready. There was a time when I wasn't. I was a lab person working in the lab, had no idea that this thing had grown out of control. And this was 15 years ago. Right, when I started working in MIT on autism for Fragile X syndrome, and that was in the late 2000s, 2007, 8, something like that. And then I was invited by Shalini Kedia.
Of course, Fragile X.
Right, Fragile X and Ummeed Clinic.
Okay.
Viva Krishnamurthy, who I greatly admire. And I think she was starting the first Fragile X clinic in her setup. So they invited me to open it. Okay. And I went. I was very happy because I'm very fond of Shalini. I admire her greatly. And I know her kids. So I said, of course I'll come. I went to Bombay and I'm about to go and give a talk on Fragile X. And she pulls me over and said, I know you're very excited of the work you're starting with stem cells, but I must warn you that this will cause a backlash. I said, what? What? I had no idea. Really tell me. He said, no, people think you're going to inject stem cells into their brains. So I said,
I thought that's what stem cell therapy was.
No, I mean, yeah. I said, what? I said, God, this is this is ridiculous. No, I'm using stem cells to understand what happens with the disease in human cells, not in rats and mice. Because how long can you keep on working on rats and mice to understand a human disease, right? So I'll come to that science later on. But the science briefly, so this was the first time I was hit by a truck. Saying, God, I'm clueless, right? I was very thankful to Shalini that she warned me. And I was ready, the questions came. So here's the thing. All of the conversations we're having about, what sort of therapies one can do for autism or for any disease, for anything to do with the nervous system disease, has been rather, slow, right? We have had a tremendous explosion of exciting discoveries in neuroscience. I'm delighted to be in it. But sadly, many of these discoveries, as exciting as they are, haven't translated into medical therapies and drugs. That's the abject failure of on all our parts. Why has it been so difficult to discover brain medicines? Heart, kidney, lung,
no time.
Yeah, cancers. Cancer is not a death sentence anymore. But neuroscience, Jesus, we are still kind of stuck, not moving.
Why is that?
Yeah, because the brain is bloody complex, number one. But that's not an excuse. The second thing is, how do we study what goes wrong in cells and molecules in a brain disorder? We cannot cut you up every time. We cannot take biopsies from the brain. People will give up little tissues from the stomach. No questions asked. You walk in, done.
True.
Unless you're opening the cranium for some other surgery, you're not getting that. So what do? We do animal models. The animals become a surrogate for the human disorders. We do the genetic manipulations in an animal, then see what goes wrong. We find something, great target, I'm excited. My name comes out in Times of India. I'm feeling like a hero. Target goes to therapy. Clinic takes years to develop a drug, first of all. FDA regulations, blah, blah, blah. 10,000 compounds come down to one compound after 5-10 years. Then you test it in a trial.
And it failed.
Or just no result, or kind of right? What we find out is humans are bad models for animals. Doesn't translate, all right? And that's a disaster.
Right.
So many people, including myself, have now said that we must start our work with human cells, not animal cells. Maybe do the same experiments, the recordings from the cells and looking at the synapses. If we start with a human cell and we find a compound that works in the human cell, maybe the chances of failure are less when you take it back to human for trials. Instead of from mouse to humans, you go from human to human.
Mm-hmm.
For that, stem cells are useful. Why? Because without touching the brain, I can just take a little drop of blood or a little patch of skin from an individual and then create induced pluripotent stem cells, iPSCs. What does that mean? These are cells, through some chemical magic discovered by the Japanese scientist Yamanaka many years ago, that you can create these cells which are pluripotent, meaning they have the capacity to become any cell in the body, in principle. And given, depending on what sort of chemical signals you give it, it will go to a heart cell or a liver cell or a brain cell.
Oh,
and that's the power, which means an individual who's affected, you haven't touched him or her, just taken some blood, and you have created pieces of organs which are of the same cellular makeup as the individual was living without touching them. And that's what we do with brain cells. So I and others have now in the lab growing little pieces of brain tissue, 3D cells, cluster of neurons that are from a living patient who happens to be in Calcutta somewhere, never seen him or her, but I have their brain tissue growing in a dish. Now I can go in there and analyze it and see what exactly has gone off, and can I find a compound that will fix the problem in the human brain tissue of a living patient. Which means whatever problems they have as a whole individual, I can see what's going wrong somewhere in the cortex or in the hippocampus, and I can replicate that in a dish, and then I can record. That's what we use stem cells as a model for the disease, the human disease. Human stem cells as a model for the human disease, not mouse or rat. Now, there's a therapy angle.
Yeah.
In some places, in some cases, one can now use these cells through very rigorous screening and lots of hurdles, regulatory hurdles, to go in some cases intervene and regenerate. See, the cells have a property of regeneration. They're pluripotent. It means that if you put in the right milieu, they will grow into adult neurons, and they're human neurons, maybe from the same individual in some cases. So, spinal cord injuries, you want to regrow the thing, right? Yeah. So can you inject and help the neurons grow back some of the connections? And in other disorders like Parkinson's, one can inject in the certain areas the dopaminergic neurons are missing. So in some areas of disease and damage and accidents, that progress has been made, and it's quite impressive. In some other cases, it might be very complicated because it's not one group of cells in one brain area that's causing autism. So where do you go, right? So that's far away in that case. It's not possible. We don't have the understanding yet. In Alzheimer's, it affects the hippocampus, it affects all of cortex. Where would you inject? Parkinson's, yes, you can. In other cases, in some cases, it can be very debilitating, rapidly declining. Somebody might die, and you might be able to give them some life in some cases. If you know the right mechanisms, everything is tested. It takes decades to get into human for some intervention in the West, right? The regulations are very strict. So stem cells as a model system to understand the disease in the human brain is vital. And hopefully in some cases where you can't take these cells in cancer therapy and other places, organ damage, like the liver generates on its own. Take off a little piece of the liver, it can still manage.
Yeah.
So that's the place where you can go and regenerate, maybe in other cases. So stem cell as a therapy is making progress. It is now realistic in some disease conditions, not generically. And there's a third aspect, which is very, very unfortunate, and I find it shocking, that still continues after decades of knowing that's happening is the scam in this country. That
Thank you for calling that out.
I shall inject this.
Yeah.
Come to my back alley in, somewhere. I've seen this in Bangalore. It's kind of shocking. It's like I couldn't believe it. I used to take photographs of them. I used to take my son for piano lessons, and for an hour I'd roam around Cooktown or something. But it's really shocking that the government didn't regulate it. And this is what's happening in the heart of Delhi.
There are a lot of parents, Professor Chattarji, who come to us and think that
they came to me too from the US.
Working.
And then we heard that you can inject this and do that. And I can understand the pain and the desperation of the parents. Some of them were high-end professionals working in top government jobs in the US. I've forgotten all the details. But, one of them, I was very impressed by him. And I felt for him. And I said, look, I'll talk to you. And then I heard about this particular therapy is happening somewhere in some city. And I said, Mr. Singh, or whatever his name was, I said, think about it for a minute. If such a discovery indeed happens, wouldn't you read about it in the front page of the New York Times? You are living in New York City. Wouldn't it happen at Sloan Kettering or Weill Cornell Medical School or maybe in Rockefeller? Would it be happening in the back alleys of Bangalore, you think? And then he suddenly realized, oh God, I'm so desperate that I've lost my common sense. So it's very bad that these people are being preyed upon, and we collectively really should call it out.
Thank you so much for really shining light on that, Professor Chattarji. And before we wrap up, I have this short, insightful segment. I'm going to make a statement and you have to say if it's true or false. Brain plasticity research offers new hope for new interventions in autism.
Absolutely, yes.
Every autistic person has intellectual disabilities.
No, I wouldn't agree with that, because in certain domains they are phenomenally skilled. Mm-hmm. And in other cases, they may not be displaying the same talent, right? So, for example, the numerical abilities, musical abilities, artistic abilities, some way above normal in some cases, right? So it varies from which circuits are functioning well and others are not. Yeah.
Got it. People with autism lack emotions.
Absolutely not.
Autism,
it is expressed differently.
Yes. Autism is caused by bad parenting.
God, this is completely horrifying. No, good parenting can help with autism. Let's say it that way.
Yeah.
Bad parenting cannot cause autism. Genes cause autism. We do not have control of the genes that we inherit. As simple as that.
Thank you so much, Professor Chattarji, for this incredible and insightful conversation. And I really thank you for taking the time to answer these important questions that parents had for you. So Dr. Chattarji, thank you so much for this incredible, insightful conversation and for calling out the scam. Also, thank you for taking the time to answer these questions that we had for you. And to our viewers, thank you for tuning in. And it goes a really long way when you like, share, comment, or subscribe. If you have any comments for Professor Chattarji, please do leave it below and we will try to get it answered for you. Till the next time, please consider watching any of the videos that are popping up in the screen. Thank you.